sometimes called the helium course because he introduced me to his guru, Professor Shavana Chatterjee, and how to extract helium from underground. Yeah, that was it. But a few people in our country don't believe us. So that's the point.
Good afternoon. My talk is completely different fare from what you have been hearing for the past 5 days. Okay, and it is so different that it's only because of Professor Sinha that it has been continuing all these years and developed as far as it has come for. So, this is discovery of a large-scale helium basin in West Bengal and Jharkhand state of eastern India. In fact, the program began way back in 1968 at the Indian Association for the Cultivation of Science with Professor S.N. Bose taking the lead of having a helium laboratory brought at the Cultivation of Science for recovery of helium from Macrocosmos. Okay, and it was actually spearheaded by Professor S.D. Chatterjee since from 1968 to 1977. He took care of this effort, and thereafter from 1985 onwards, it is Professor Sinha who has really nurtured the project. It is a very important project, all said and done, because of its implications to many industrial and scientific activities, as you shall see after a little while. Now, helium has got a number of applications all through the human interest areas. That is, whether it's in research or electronics or aerospace industry, medical, in fact, science, they use a lot of helium, and of course science research. Now, what has happened is, of late, helium actually has been recovered so far from petroleum gases, but new petroleum fields have not really come up with any helium as of any consequence actually. So this has resulted in shortages of helium, periodic shortages of helium, especially since 2010, and the fact is that it is getting very critical at times to get helium from various sources. So this has caused interruption in hospital services, science research programs, various industrial applications. Okay. And so given the importance of helium to modern science and society, there still is no exploration strategy as such. Globally, there is really no exploration strategy to recover or search for helium from different areas. Now, the major consumption area for helium is the medical. In the MRI scanning, which takes about 30% of all the helium consumption worldwide. Then comes petrolating gases, that is in space research, then analytical and laboratory applications, welding, engineering and scientific, leak detection, semiconductor industry is now taking up a lot of helium. This is likely to, this is likely to increase very rapidly because all the semiconductor chips, all your mobile, etc., all these devices, they require a lot of helium for their fabrication. Helium actually is presently derived from petroleum gases. Okay. Now,
I'm sorry to interrupt you.
yes.
You didn't mention the most important area of helium, space and atomic energy.
I did mention space. Okay.
Atomic energy, ground atomic energy.
Yes, atomic energy also.
What is the space application percentage-wise? Space and atomic energy?
Yeah, space actually, they require as a thrust gas for the hydrogen and oxygen fuel. Okay, when hydrogen and oxygen is combined to give you the thrusting power, so there is a depletion. In fact, there is liquid hydrogen, liquid oxygen, and it has got to be pushed by inert gas helium. Otherwise, there will be back suction. Okay, so helium is required for that. Now, the petroleum gases sources is actually helium arises because of the interaction of methane or radioactivity on methane actually at depths of temperatures that are available in the depth of the earth, temperatures and pressures. So whether it's biogenic helium or methane or biogenic, okay. So normally you see 1 cubic feet of helium is associated with 400,000 cubic feet of methane, weighing 8 tons, and that goes on to create further petroleum gases. Now, worldwide producing countries, US is the highest. In fact, it's about 55%, followed by Qatar, 32%. Rest are minor producers. Okay, Australia, Algeria, Russia, Poland, and the rest of the world, 1%. Now, lately, the USA Federal Reserve helium has been stopped for export. USA had been acquiring or rather conserving helium since 2002 to 2016. They have been conserving helium in their depleted oil wells, and that now they have stopped exporting from that source. Okay. So that there is a rise in temperature. Sorry. Yeah. So there's a rise in the prices of helium, and you can see this graph how steep it is. In fact, one has got to now dig much deep into the pocket to purchase helium. Now, you see, this is a structure of the Earth. And if you see, the top crust is just about 30 to 50 kilometers, average about 40 kilometers. That's a thin, this is thin layer, okay, just about 38 to 50 kilometers, 35 to 50 kilometers. And this is all where the current day petroleum gas is exploited. Okay. Whereas in the mantle, which is contains about 68% of the Earth's volume, this is very much enriched in helium. Okay. So, it would be prudent to look for areas where the mantle helium is escaping. Now, there is a helium leakage from the mantle at several places where there is rifting of the continental basement resulting in deep clustered gas release in the form of high nitrogen gas seeps containing about 1% or more of helium. And in India, this is the region where it happens. This is what is known as the Son Narmada Tapti lineament. Okay. This is about 2,900 kilometers long and the Son Narmada Tapti lineament about 2.5 kilometers from the surface, and it is a 35 to 38 kilometer deep wedge actually running to 1200 kilometers east-west across the belly of India. It is in fact the second most important tectonic feature of the Indian geology after the Himalayas. This is also the seat of very large number of earthquakes. Now, we are looking at a place where we are working, that is in the Takloi-Bakreshar area. This is an area which was manifested by a volcanic event lasting for about 60 million years. Okay. From 120 million years back to 60 million, this is a volcanic area, and the area that we are working is here. Okay. Now, if you see the crustal depth here, normal crustal depth is about 40 kilometers, but at this place it is about 25 kilometers. Okay. So, with the crustal depth lesser, so you have got a high geothermal heat, that is 240 milliwatt per meter square per second, that is 3 times the global average, about 60 or 65 milliwatt per meter square per second. Okay. Then the crustal thickness also is much less here. It is 24 kilometers against 38 normal kilometers. And the density of the overlying rocks is about 4% less. So all these three factors give rise to the conditions for helium to escape from the mantle through the crust into the atmosphere. So this is a pictorial diagram, okay, for radon and helium transport. So this is the area of uranium. There's a uranium belt here, and then the gases active fault system. The gases come out from here and from various places and go up. So this is the picture of the helium transport, because there are a number of hot springs in that area. So these hot springs actually they scavenge helium from beneath outside. And if you go through various spaces, you get various concentrations of helium at various sites. So there are large number of thermal springs in that zone with temperatures close to about 70. So with helium concentrations much more than 1%, almost from 2% to about 1%, and then the rest of it is nitrogen. In the case of petroleum gases, it is mostly the petroleum and methane. Here, the amount of methane is much less. The nitrogen is very high, showing that it is coming more from depths rather than from the petroleum gases. And these springs are about from Bakreshwar to Jaro will be around about more than 1,000 kilometers apart. So this is the belt starting from here, West Bengal, it goes here and ends here. So this is the geothermal belt, and this is the helium belt also, the same region. So anywhere you pick up gas from the soil, you can find helium in that soil. So we have been working in the Dubka district, and this is a satellite map, and we have focused in a small area here, and these are the fault lines, that is the discontinuities in the Earth's surface, these yellow lines, these are the discontinuities in the Earth's surface, this is the long discontinuity, these are the rivers, various rivers here. So this is the gas sampling site, and it's a beautiful site actually. Rural India is really very beautiful. So what we do is probe about 1.5 meter long is put into the earth. In fact, it has got to be hammered into the earth, and then you have got a system by which you can draw the gas from inside, you pump out the gas, so you get the soil gases here. So this is a experimental arrangements, okay. And these areas actually you have got to first dig about 6 or 8 inches beneath, a little bit here, and then put the pipe in, and then pump it out into a common cylinder, and then analyze the gases. So this is the profile. You find helium in these regions where it's darker, okay, up to 1350 parts per million in the soil air. This is a three-dimensional figure of that. In a larger area, 15 kilometer by 22 kilometer, and you find these are the high helium areas. And if you insert your probe, or if you take up the sample from here, you get a high amount of helium in the collected gases. And recently there was drilling by the Atomic Minerals Division, and for us to collect gases, we did collect some gases, but unfortunately this was a standard drilling rig used for uranium exploration, and it did not have a proper channel to withdraw the gas, so there were some difficulties in sampling the gas. But normally, what happens is if you go at different depths, you get profile as you go beneath, the concentration of helium will increase. Okay. Normally, but this figure, of course, does not belong to the previous one. In fact, this is just a normal profile. Now, in the field, we were able to collect the sample gases to extract the helium, and it was possible to do so. In fact, what we used was liquid nitrogen as a coolant, pressurize the gas, and condense the oxygen and nitrogen and recover the helium from it. Yes? Yeah. So, now if you want to have a connection system, you insert a large number of probes here, transfer the gas to a compressor, into a gas holder, gas tank, then again, at this stage, of course, whatever moisture has been collected will be unloaded, and then you compress it further, pass it through a drying unit, and then to an enrichment unit, and then further to an enrichment unit. And this is the schematic diagram of the system. So, the amount of helium that is escaping, this is the actual data taken, is about 1200 ppm. The 3 meter cube per hour per meter square is the outflow rate, and the quantity that is escaping per meter square per day of helium is 0.08. And if you integrate it onto a surface area of centimeter by centimeter, approximately 5,000 meter square, you get about 432 cubic meter helium per day, equal to 61 cylinders, okay, of 7 cubic meter capacity. Yearly it would be 22,525 cylinders per year. So the energy cost of course, helium is less. The higher the concentration, the lesser the amount of energy you waste on separation. And in this case, the cost would be about roughly 75 rupee or 75 kilowatt hour per normal meter cube helium separated. Now, this is the profile. You see the helium picture, that is, now we are somewhere here. Okay. But within 1 year, 100 year, you will get no helium